Okay, so today we're very happy to have Herbert Gangl from Durham University, and he will speak about Zagier's Polylogarithm conjecture.
Thank you very much for this invitation. I'm extremely happy to try and present a kind of historical talk almost. So there have been a couple of new results in the recent past, but as I presumed that not so many people are familiar with the whole settings, I decided to start from what I consider the beginning. So it's going to be rather idiosyncratic in the choices, so I may have missed out bits here and there. So there's just a reflection of what I think I know, and what I don't know are probably the things that are missing. So the title on Zagier's Polylogarithm conjecture, so that goes back quite some time now. And it all started indirectly, at least, with Dirichet's class number formula. So the analytic class number formula for a number field. And I try to recall I'm sure almost everyone knows it almost by heart, but I just establish some conventions here as well. So that relates fundamental arithmetic invariants like the ideal class number and the units, the size, a measure for the units, and the number of roots of unity into one single value of an important function, and the function is the Dedekind zeta function of the corresponding number field. So denoting, as usual, the n of I, the ideal norm of an ideal, then we have, of course, the Dedekind zeta function defined as the sum over those norms, which is always defined for real part greater 1, and we can even extend it to a meromorphic function away from the point s equals 1, where it has a simple pole. We can also use the functional equation where we relate zeta s and the zeta 1 minus s as usual. And so the upshot, so the most concise way of stating this analytic class number formula, I believe, without too many extra bits, is this following the boxed version here. So if we denote zeta f star of 0, the first non-vanishing coefficient in the Taylor expansion, then this is related to essentially the product of product here of the class number of the regulator attached to f, and here we have the number of roots of unity w1 of f also entering the game. So so here it says R1 of f can be written as the co-volume attached to the roots, to the units. And what do we mean by that? We first take the units, the group of units in the number ring, and map it via different embeddings of the field into the complex numbers, and then evaluating by the logarithm of absolute value of those elements in C. And those altogether give us a matrix of which we take a minor, maximum a minor, and that is essentially the regulator. The crucial thing here is class number times the regulator. So this is annoying. Okay. And I would like to now go to higher analogs. So the prototype of the formulas that I'd like to discuss is the one that we just looked at, zeta f star and 0. And we want other evaluation, for instance, at -1, so at 1 minus m, 1 minus m in general. And can we say something similar? Do we have an arithmetic interpretation? And in general, so we can re-ask, kind of, is there a relationship? Is there a relationship that we have zeta f star at 1 minus m written in terms of higher class number, something like a higher class number times something like a higher regulator? And the twiddle still somehow needs some specification. And there's originally similar work by Borel showed that we have the rank of all the relevant algebraic groups, algebraic K groups, attached to a number ring. And they will play a kind of the important role of the units and class groups. We have higher regulators arising from a certain type of algebraic K group, and then there is a regulator attached to those odd-indexed algebraic K groups. Unfortunately, this is rather abstract. So, in a nutshell, we can. He showed. So Borel, in his seminal papers, showed that the rank actually is 0 for the even-indexed K groups, and for the odd-indexed ones, we call it Tm, and it depends with the parity of m. So it's either R2 if m is even, or R1 plus R2, where R2 is the number of pairs of complex embeddings, complex conjugate ones, and R1 is the number of real embeddings of that field F into the complex numbers. So that kind of is what already was known in 74, 78. And a more precise version was given by Lichtenbaum, and he actually asked whether this can be refined. So this already was recorded in 72, so even before Borel's work was published, but he actually relied on insight of Borel, and this was in the Proceedings volume. But he quickly found out that, well, this this higher class number, which would not have any direct input from Borel, he had the idea to have the order of a specific algebraic K group as well, and in fact an even index one. So the odd index ones play the role of this regulator part, and the even index ones, one lower kind of, play the role of the higher class numbers. So that was at least his suggestion. And here the twiddle again, up to known factors like powers of pi and certain known rational numbers that might enter the game. Now the question, how does that reconcile with the original Dirichlet class number formula? It turns out that we have K naught of OF having one component, which is the rank of vector bundles in K theory, which we can ignore here. We're interested in the torsion-free, in the torsion part, which is the class group of OF. And we can interpret HF here as the class group of OF, the size of the class group, and therefore we can rewrite it as the order of K0 OF torsion. And in a similar way, K1 OF is simply the units in the K1 of a ring is simply the units in that ring. And then R1 of F can be written as the co-volume of K1 of OF. So therefore we can rephrase it as zeta F star of 1 minus m being roughly the product of the K group K2n minus 2 of OF and the size of K2n minus 1 of OF. Well, we divide by the torsion here to have a nice, to guarantee a nice map into a lattice, but essentially K2n minus 2 size times the size of K2n minus 1 is what we should keep in mind. And I was not able to find the original, which I wanted. So the Lichtenbaum's explicit quote. He simply asked the question, but now it has become Lichtenbaum's conjecture. Okay, so is there such a relationship? So Bloch's work amounted to getting rid of the abstractness, in a sense. So those K groups, you may have seen that the typical definition of a K group is in terms of take the limit of GLN into GLN plus 1, stabilizing. So that gives you GL. Then you take the nth homotopy. Then you take, first you take the plus construction, then you take the homotopy, then, and this essentially gives you the K groups, but then you have pretty much lost the chances of making things rather explicit. And the only one that I'm aware of, actually, has been, which gives Bloch's original regulator in the case of K3 of F, is the one by Chu, Malan, Sanchez Garcia, and Snaith. And they've looked at one of the very simple cases, the simplest possible almost cases where you have a non-trivial regulator. And even there, they were not able, I think, to even give a single reliable digit, only an interval, bounded interval between which the final result would land. So this is a very hard approach and possibly impossible to ever get going. Then Bloch actually, and I only just realized that he got the Steele Prize this year, end of last year, but for this year. He had these famous lecture notes, which he had written in 1978. I believe, an urban legend, maybe that he submitted it maybe to the Publication IHES, and I presume that the referee, well, I would guess, obviously it was Borel, was not happy and wanted to rewrite, which Bloch was not willing to do, and eventually they were published in the original form in 2000. And they have been amazingly influential, despite the lack of actual publications already to that point. And in those, he established the first candidate for K3 of a field. So this was not that there was nothing known at all apart from the abstract construction, and he came up with an idea, and even together with an associated map, which then turned out to play the role of a regulator. So the idea is to study the kernel of the following map. So this is maybe of interest. So this is the crucial map that we'd like to understand. So take the free abelian group on a field and you map it to the wedge product of the group of units of f, so simply f minus the 0, wedge with itself. And yeah, maybe 0 does not really have a definition, so we simply put it to the 0 in this group on the right-hand side. Same for 1. But for all the others, we take a generator, call it x with x and f, and then we take x wedge 1 minus x. And the surprise is that having sort of the addition here combined with the multiplicative properties, because we view this difference between 1 and x as an element in the multiplicative group of f, this lets all hell break loose. And lots of new kind of strange arithmetic or arithmetic properties ensue. So the point is to study this kernel and ignore whatever there is, whatever comes from universal elements in the kernel. So which are which not really point to anything in f, but they come from general phenomena. I'll say about a few words about those in a bit. And the expectation now was that taking the kernel of the map here, taking the kernel of this map and dividing by a group of those universal relations, so generated by those relations, let's call it B2 of f. Later on, it took the name Bloch group. So Bloch already expected that this is a close, in close relationship to K3 of f. And indeed, Suslin, not that far later, actually confirmed this, and he even established a rather precise relationship between K3 and B2. So it's a surjective, essentially, relationship. Here we have a torsion group. So that he gave this short exact sequence with a modification maybe of B2, but let's not worry about any details here. And in particular, those groups have the same rank. This is torsion. Now, just to give you a feel for...
Sorry, can I, sorry to have interrupted you. Ich habe eine kleine Frage. K3 in the middle should be K3 indecomposable, if I clearly understand.
Yes, you're right. Absolutely. Thank you. Okay, so-called K3 indecomposable, which is sort of a piece of K theory, but even then the ranks will not differ, so it has the same rank as the B2. So it's also, there is something like a simpler part, as some people call it, so K3 Milner. So you have the quotient K3 of f by K3 Milner, and this quotient will be the correct one, indeed. So that is wrong as it stands. It should be K3 indecomposable. Thank you. Okay. Yeah. So let's try a few elements in that kernel. First of all, I claim if we take f equals q, then the element 1/2 lies in that kernel. Well, just because a wedge A is put to 0. Similarly, if we take any x in Q, and we take x plus 1 minus it, that lies in the kernel, say up to maybe, no, this lies in the kernel. And this version here, well, up to some small torsion, let's say 6 or maybe 2 is I think 2 is good enough, but up to small torsion. This is also in the kernel. A bit more interesting is the next one, where we take 9 minus 6 times 3. So there's something you might be able to do in your head. So where you take, so let's try maybe here. So 9 goes to 9 wedge minus 8. 3 goes to 3 wedge minus 2. And then you realize that minus 8 can be written as minus 2 to the power 3. 9 can be written as 3 squared. And if you have exponents, then you can pull them kind of in front and then multiply together to the 6. It's given here. So that gives you part of the idea of what's going on. But the next one is maybe more interesting, because it actually uses real relations. I mean, very more complex algebraic, more interesting algebraic equation relations. So in the field f being q root minus 7, look at the number given here. Number given here, which is the root of this polynomial. So therefore it satisfies, if we take alpha squared plus 1 minus alpha together, add it up, comes minus 1. And therefore dividing by alpha squared, we get the next equation. So here we have something of the type of 1 minus an element in the number field equals, again, such an element. And if we now use, as before, the sort of expansion, if we have a wedge B, then we can write it as the sum of a wedge BC, then we can write it as the sum of a wedge B and a wedge C. We can kind of treat each tensor factor as if it were a logarithm, pull it apart with an addition. And if we work modulo 2 torsion, that only amounts to ignoring signs in individual wedge factors. Then we get the following. So claim is taking minus 1 minus alpha over alpha squared. It goes to x itself, so it's minus 1 minus alpha over alpha squared, which is this multiplied by that. So here it's plus. So and those two together, so this becomes 0 because a wedge A is 0, and power 2 comes in front, and we can ignore signs. So we'll wind up with minus 2 times 1 minus alpha wedge alpha, which is the negative of the same thing if we had alpha wedge 1 minus alpha, which is the image under our map delta 2 of alpha here. Overall, this combination lies in the kernel of that imaginary, of delta 2 for that imaginary quadratic field. And so you can see sort of roughly how algebraic relations kind of figure into not uncomplicated way to write elements in the kernel. So let's look at universal relations. So things that are true for all fields. Suppose you have a Zi in a given field, 5 of those, and satisfying following relation. 1 minus Zi equals Zi minus 2 times Zi minus I plus 2, and we take the indices mod 5. Then the claim is that the sum of these actually, and it will be periodic, 5 periodic. That's a not quite trivial claim, but you can do it. And then the sum of those also lies in the kernel of the corresponding map. And this is an avatar of famous 5-term relation. So now this points to the following function. Block the dilogarithm is a function that vanishes on those universal relations. That means it has it satisfies 5-term relation as a functional equation, and it is given by a variant of Euler's dilogarithm function. So Euler's dilogarithm function is simply the simple power series expansion around so in the unit disk, which one can then extend to a multivalued function in the whole complex plane, with a few points sort of exception, but which can be made sense of course. And we take a single valued variant of this. The problem being, just like for the logarithm, Li2 of z has monodromy. And in order to kill that monodromy, one looks at a function that satisfies similar such a monodromy, which is this one. At least the imaginary part will match the monodromy of Li2 of z itself. And this was originally studied by David Wigner, and then Bloch could rely on his studies in his famous lecture notes. So L2 of z now can be extended to a function on the quotient that we defined as B2 of f, and therefore it might play the role of a higher regulator for that K group which this B2 of f is supposed to represent. And by Suslin's result, we can essentially think of B2 as an avatar of K3 of f, modulo the decomposable thing. And indeed, we should also give think credit to Goncharov for for some part of this. So it's been proved in the case for m equals 2, which I should put here. So for m equals 2, we get here pi to the power 1 times the d2, which was essentially the R2 of Borel's rank determination. So the theorem was that for a number field f, get sufficiently many elements, psi1 to psi R2 in that kernel, such that their images under the dialog give that first non-vanishing coefficient in the power series expansion of zeta f star, up to power of pi, up to a rational number. And so it was folklore at the time that Borel and Bloch and Béhanzin altogether and Suslin would imply the same thing that Zagier proved, well, in a slightly weaker form, where he had to pass to some extension field of maximally degree 4 larger than the original one, but so it's very close, plus an epsilon, which I think Goncharov was the first to really put things into the right context, into one piece. And overall, we can say Zagier's Polylog conjecture holds for n equals 2. Now, a more precise version of that also takes Lichtenbaum's suggestion into account, but only for abelian fields, was shown between 1995 and 2003. Originally, Kolster, Nguyen-Quang-Do, and Fleckanger had a version, but with erroneous Euler factors, which then were corrected by Nguyen-Quang-Do and Benoit. It was also proved by Huber and Kings, and then also by Burns and Greiter, in context of Tamagawa number conjectures. But all of these were given up to a power of 2 only. And in a recent update, kind of, joint work with Burns again, Zagier, Ram, and Yasaki, we showed that the power of 2 can be settled using the seminal work of Flach. And this actually allowed us, so there's a kind of byproduct that I wanted to share. This allows to derive the first genuine generators of that group K3OF for some imaginary quadratic fields. Before, everything was up to torsion. Potentially there's something missing for a generator, but now we can actually give a generator, but of course in the setting of this group B2 that we replace K3 by. And then for the following field, Q squared minus 4,547, just to give an idea, then we have this element here. Oops. This element here, where we put omega equals the 1 plus root minus d over 2. This linear combination gives an element in K3OF, and it is a generator of the torsion-free part. The fun thing about this is that the corresponding group K2OF, as I said, they always come kind of in pairs. This has order a large prime. This is the first big prime, I think the smallest discriminant for imaginary quadratic fields where this prime ever occurs. So this is just a little illustration of what one can do if one knows Lichtenbaum's conjecture, and for this case, this has been settled. So far we just have dealt with weight 2, but now what about higher weight? How can we generalize this D2 and the corresponding, for instance, for delta 3? What is the candidate for, I should add delta 2F. What is a candidate for the higher K group K5, the next one? And indeed, Zagier in the late 80s defined a higher block group. And on this, he also gave a single valued version of the next in line, so the trilogarithm here, which plays a role as a regulator. Regulator for us means it maps to a lattice in some R vector space. So you have a group which you may have a hard time associating a volume to, but then once you map it into a lattice, then it's obvious you take a fundamental mesh, and the volume of that fundamental mesh will be the co-volume of that lattice, and a very good measure for you. Lattice. And in the first approximation, he mimicked kind of this fingerprint map from before that I attached, associated to a Bloch, but which was in a similar way already dealt with in algebraic K-theory before, I think. And so he took the same x wedge 1 minus x from before, but extended by another tensor factor x, again taking a copy of f cross tensored with the original one. And this time the kernel is not good enough for what one wants to define. The case of f totally real was still okay, and that's where Zagier originally found examples which seemed to work, but then they didn't work in other cases. So he needed to impose further conditions. And the further conditions come from kind of the fact that any homomorphism from f cross to z that would sort of map from here to z tensor lambda 2f cross, which then we can identify with lambda 2f cross, tensor is over z. So each such homomorphism induces a map from the kernel of this delta 3 to the kernel of delta 2. And we can do that for each tensor factor. So there are still further things to take into account, and the demand was, and this was inspired, as Zagier writes, by Delin, that you should land in the intersection of all these kernels. So you take the kernel of those maps and the intersection of all these homomorphisms. That should be the right thing to go for. And then again, one can define a subgroup of universal elements. This really doesn't seem to work well. Well, I'm stuck here. So, okay. And one takes the quotient of the group A3 of F, this intersection of all kernels, by the set of, or by the group of all universal elements. And then this was essentially this candidate for K5 of F, or K5 of OF, as it turns out.
Sorry to have interrupted you. What do you mean by intersection of all these kernels? What do you mean by these kernels?
So take
At the moment, I see only one map.
Yeah, so for each homomorphism here, you get a map from the kernel to from the kernel of delta 3 to the one of delta 2. But there are many such homomorphisms. For instance, for each prime, you can evaluate, take evaluation for each prime, for instance.
I see. Okay, thanks.
And you can do it also for each of those tensor factors, right? So there are quite a few maps that you have to take into account in principle. But essentially, I think for this step, it's even sufficient to look only at the map from the first tensor factor rather than for the individual ones, and then take those into account. And there's a much better way to write it, and eventually Gonchar found a way to very conceptually formulate it. But let's try to follow the old route here. So a function that is defined on that quotient is a single-valued version of the trilog. We just saw the trilog as this formal power series with z to the n over n cubed. And L3 of z is again, so this time the real part of a linear combination of Li3 and Li2 times Li1 and Li1 3 of Li1s. And this has been found, or a corresponding one has been found for any level m greater or equal to 2, first by Ramakrishnan. But that was kind of still implicit, and it's been made explicit by individually by Wojtkowiak and by Zagier. So this now is a good function on that quotient A3 by C3. And you can iterate that process again with these homomorphisms from F cross to Z, all combined, and trying to make sure that all those that they land in the kernel of all of these on the intersection. Then you define a higher block group Bm, and they should play the role of the corresponding group K to n minus 1 of F. And then we can formulate the gist of his original conjecture. Actually, this is a corollary of this. Once you have the two kind of matched by his original conjecture, then the polylog conjecture ensues. And it says, essentially, for a number field F and an integer m greater 1, there are sufficiently many elements psi j in those groups am of F. And the number of how many one wants, this is our dm. So that's the rank of the corresponding group kn minus 2 OF. Such that the zeta value, the first non-vanishing term of the zeta power series expansion, is related to a determinant of Lm. And here the twiddle indicates the power of pi, which we've seen already in, I think I wrote it on the first slides, and a rational factor which did not figure in this polylog conjecture. And sigma runs through all the appropriate field embeddings, depending again on parity. Either it's R2 complex embeddings without complex conjugates, so avoiding complex conjugates, or taking those together with their real embeddings, depending on what the rank, what Borel's rank computation tells us. So essentially, this is the kind of phrasing that we'd like to say in a rough analogy: zeta f star, and the determinant of those higher polylogarithms, m logarithm, evaluated on higher units. So that's, here is the higher regulator, evaluated on higher units. And this should somehow be seen by the Dedekind zeta function at 1 minus m. Now, Goncharov had a vast program. He entered the stage shortly after, so if I recall correctly, was the end of the 80s when Zagier put his conjecture into print, and then Goncharov had an ingenious new point of view. So what he said, let's study configurations of rather than 4 points in the projective line, he took 6 points in the projective plane, and he wanted to associate a trilogarithm value to each such configuration. So these are under modulo the action of PGL3, these configurations, and we want to give it a trilogarithm value. And he succeeded, and showed that for m equals 3, this really holds. In the process, he found a new functional equation for the trilog, and so he gave a new projective invariant for a configuration in the above sense, 6 points in the projective plane, and this has been dubbed the triple ratio. We can picture it if we indicate each point of, say, 6 such by their index. So here we have 1, 2, 3 correspond to point P1, P2, P4 here. And this is the determinant, a 3 by 3 determinant where each vector is sort of represented by 1 in A3 in the affine space. Then we multiply 3 such 3 by 3 determinants together in both numerator and denominator. We'll find that this is a homogeneous expression. So as many ones in numerator as in the denominator, and same for the others. And we alternate this expression. And this is his triple ratio that you attach to a 6 point in the projective plane. And then you can evaluate by that single valued version of the trilogarithm, Li3. So if we evaluate Li3 on that, then it has the property that it represents a say, continuous co-cycle for the group GL3, factor 5 co-cycle. And this is a different way of writing, claiming kind of Zagier's conjecture. Once you have corresponding continuous co-cycle of the right, in the right cohomology group, for the right group GL. So it's GLM. So in general, we have GLM, and we need a 2n-1 co-cycle. Then this also gives Zagier's conjecture. But unfortunately, it's not as simple as that in general. So more conceptual way that Goncharov proposed, and it was just as well more detailed, more refined. He not only looked at K groups, but he took the it's called the graded pieces, the Adams grading. So there we, for instance, like in the K3 indecomposable, can be identified with what's called K3 upper 2, so the Adams graded piece there. So he had a more refined version of this, resulting in motivic complexes or polylogarithmic complexes, and even a vast motivic co-Lie algebra, which was at the time conjectural, motivated, I think, also by Bailonson beforehand. So that should be attached to any field, not just to number fields as in Zagier's situation, but for any field. And those polylog complexes have much more detailed information as amazing new type of insight. So he had this vast program, and I really call it very visionary. So he had many tools that he suggested how to attack Zagier's polylog conjecture for higher weight as well. In particular, he suggested to look for these higher cross ratios. And despite his quite tremendous progress, he even got a medal in Paris in '92. The same approach for m equals 4 has not yet been successful. And Gangl famously wrote the reason being that 4 equals 2 plus 2. Okay. So something new is going on in weight 4. That was the gist. And so he suggested to also invoke multiple versions, multivariable analogs of the original polylogs. So they're called multiple polylogs. And the simplest ones in depth 2, here we have the depth kind of counts the number of variables. We have AB of xy simply given by the double sum, but restricted to a cone. The summation is restricted to a cone. And then he singled out a combinatorial problem that would help quite a lot already in finding possibly a solution for the conjecture in m equals 4. So if you write the 5-term relation, I mentioned it before as a 5-cycle relation. Let's call it v of x y, a v for the Roman 5. Then the conjecture was that if you plug it into that Li31, well, a version of it. So I31 is essentially a version of Li31. If you plug those 5 terms in individually and you take the sum of those 5 terms, shorthand I31 of fix one variable, but let the other variable go through the sum of 5 terms. Then, so essentially plugging in the dilogarithm relation here. So if this expression should somehow not be true in true depth 2, so here the depth, the 2 variables, but actually should only come from a function that has a single, that depends on a single variable. And the function should be Li4. So that was essentially his insight. Well, modulo, maybe one should just say modulo products of lower weight, but let's not worry about that. And it should be a finite such sum. So this seemed to be quite approachable. So you could phrase it in such a rather, say, innocuous looking way, and was easily found for a functional equation in one variable. Zagier had it sort of within a day, I think, one of them. And I found a whole family for which that works, but that's still, it's not good enough. And Gangl was not happy enough. So we really need this full 5-term relation. Now, in the meantime, Gangl kept getting more and more important results that he showed, for instance, that the co-cycle condition that I said essentially implies Zagier's conjecture, he could reduce to a multivariable version of the polylogs, which he called the Grassmannian polylog. And he showed that this actually does it. So it now remained to produced a Grassmannian polylog to that one variable function LIM. Then he established the Motivy-Coley algebra for number fields, worked with Dili. Then he studied the connection to cluster algebras, which seemed to be a bit far-fetched. And in particular, he gave a symbol, an algebraic fingerprint for all these multiple versions. Generalized the delta M. I haven't given you the definition of delta M, but essentially it's the previous one. It's just instead of X tensor, X weight 1 minus X, can replace it for general M simply by thickening this X. So you take several factors, the X tensor M minus 1. So, and a more complicated version of that is has to be with not just a single term, but with many terms. Makes life considerably harder, but it gives you a better grip on those multiple versions of polylogs. Maybe I think I'm almost out of time already, so let me maybe skip this. So roughly, we can think of it as a sum of such elementary tensors capturing the differential behavior of the function. And all these ingredients actually, as I indicated, eventually actually helped in his joint proof, in his proof of Zagier's conjecture for the next level. We come to now. There's one more thing. In collaboration with physicists, they reduced a huge calculation that Durham and others had done for, well, we don't need to know that, 6.1 loop remainder function. So 6 external momenta and 1 loop. And this is in n equals 4 supersymmetric angles. So whatever these words mean, they could drastically reduce the whole thing from 17 pages to essentially one rather long line and a few conventions. This triggered a collaboration of mine with Duo, the same person who actually had the original hideous-looking expression, and we reverse engineered their results because they only had a very short 5-page note, and so we found a way to justify it for ourselves. Turns out that it was more complicated than their original one in the end, but as a byproduct, Duo implemented that symbol in such a way that I could experiment for a month on end, and in the end, this actually turned out to be fruitful, and we could solve. Actually, I could solve the conjecture of that Goncharov had put. And as a side note, I found that a few days after Zagier's 60th birthday celebrations, unfortunately a bit too late. So one can get by, I claim, with 122 terms of rather complicated nature, and the conceptualness is not really guaranteed. Now I'm skipping maybe just to get to the last stage. So in 5 years later, actually 6 years I think later, because Zagier's 65th birthday celebrations with modular forms being everywhere was, I think, delayed by a year. Goncharov gave an invited talk, and he actually announced yet another point of view on the original problem, this time using these cluster algebras in terms of complexes, moduli spaces, new concept of motivic correlators, and so that together with the Rudenko, they had a new relation that they denoted Q4, and that related those new motivic correlators that roughly played the role of I31 and Li4, as in the conjecture that I put forward from Gonchar earlier on. And this plays a role that is almost more central than the 122-term relation. In principle, they could probably derive this 122-term relation, but they never needed to. So let me skip those. And they established the connection to algebraic K-theory so that they can now claim, that was in 2018, that Zagier's conjecture holds for m equals 4. And what they did not yet do was to make this explicit. And their approach they might be hard-pressed to make that explicit. And we were able to do that with Charlton and Radchenko. And so we can now claim that there is an explicit form of that quadruple ratio. Yeah, let's skip that. Just to show how complicated it is, it eventually consists of 368 orbits under the action of the alternating group on 8 letters. So it's nothing you want to do by hand. And moreover, we found, we tried to use that approach of Gonchar and Rudenko and push it to the next weights for m equals 5, 6, 7. We also had can now claim to have suggested analogs of those crucial function equations, and hopefully they help in finding more relations for more results for Zagier's polylog conjecture in those weights. And very recently, I would be amiss if I didn't mention it. So just half a year ago, an amazing preprint by Rudenko solves yet a further conjecture by Gonchar, where he reduced the depth by a factor of essentially 1/2, which is quite astonishing. And there they announced similar results to our QMs above, joint work with Andrei Matveyakin. So that was all I wanted to indicate. And I'm sorry if I rushed things through, and hopefully there weren't too many mistakes. Thank you.
Well, thank you, Herbert, for a beautiful talk. I'm sure everyone is applauding. It's just that it's Zoom, so no one hears. Any questions, anyone?
Would it be possible to share your slides?
Yes. Like, do you have a specific one in mind? Or you mean the whole thing?
No, just the whole talk was, yeah,
Sure.
the whole thing was great. I mean, it was a great talk, and it's nice to have all these things sort of packaged in a way that you see the overall picture. It's great. So
yeah,
but it'd be very nice to have this in one's drawer and be able to think about it every now and then. So
I should correct the mistakes that Grigory.
Okay. Well, yeah. No. Yeah. Okay. This is not an issue.
Yeah. Of course,
we promise not to post it on the internet.
Maybe I can ask a question to you instead. So you had, I think, I heard of Kudla's dream that you wanted to say something about this second term in the power series expansion of the Dedekind zeta, say, function.
Yeah.
Has there been any progress?
Well, I mean, I guess the point is somehow that the say the Beilinson conjectures about zeta functions always refer to the leading term, right? So at the center where you get some vanishing, then you get some regulator of something, right? Mm-hmm. But I think that based on the structure I'm getting by looking at, so somehow my motivation was to look at Eisenstein series and integral representations of these various L functions that one's talking about. And then when you look at these integral representations, there's some Eisenstein series. And then one's often led to see that it's not just the first term, but the first two terms of the Eisenstein series that seem to have some arithmetic meaning. And so in the paper with Rappaport and Yang, we have a paper where we look at Shimura curves. So just the usual Shimura curves. And on Shimura curves, of course, you can define the analog of CM points. These are points where the abelian surface has extra endomorphisms, right? So that's just the analog of a CM point. And you can ask for the number of such things. And so it's given by some modified class number, a la Henri Cohen. I mean, it's similarly to the fact that the CM divisor on a modular curve is just given by some class number. So that's a degree of that zero cycle. But if you look at, and so this degree occurs in the first term of a series expansion of an Eisenstein series. The Eisenstein series has weight 3/2, but we're not looking at the center. We're looking at the off-center point, which would be called the Tate point for the motivic type people. It's like half away from the center. So it doesn't vanish there. And the value of that, if you look at the Fourier coefficients of that Eisenstein series at that point, you get just these degrees of the CM cycles, right? Just the usual degrees. The number of complex points in that divisor, right? Usual over C. But if you look at the derivative, in other words, if you look at the next term in the Laurent expansion with respect to the variable S, these are Eisenstein series involving an S. If you look at the next term, you see the Faltings heights of these abelian varieties. You see, so these CM points correspond to some abelian surfaces with extra CM or something, and they have Faltings heights. And they're essentially, because they have extra CM, they're isogenous to a product of an CM elliptic curve times itself. Just isogenous to, but in any case, they're related. And then the next term in that Laurent expansion is the Faltings height. So you see, this is a situation in which, if you look at, but morally speaking, if you look at the analog for Beilinson, you would only be looking at the degree of the zero cycle. But the Eisenstein series is somehow showing you that the next term has some arithmetic meaning as well. And so the general idea was that why shouldn't this also be true in the context of zeta functions? In other words, for zeta functions, we often just look at the first term and say, okay, it's a K group or it's a whatever it is. But I think it makes good sense to look at the next term for these guys. So that was and we had some examples, the one I just mentioned. And then there's recently some work in the function field case where they really have found using Stuka and these et cetera. I mean, very fancy schemes in characteristic P. In other words, if we go to the function field analog of this stuff, they find interpretations, Wei Zhang and other people find interpretations of all the derivatives. The whole power series is related to some kind of cycles on some moduli stack of these things. So of course, this is function fields, and we have no idea how to do any such things for number fields, but it indicates that it's not silly to look at, to ignore the fact that the leading term isn't zero and to look at succeeding terms in the expansion. I mean, there's one example which Tonghai Yang and I haven't written up yet, but we've been meaning to for some years, and that is that in Floch's work, he has some place where he's looking at a symmetric square L function, and its value plays some role in his calculations, right? But we have a formula for the next term in that Laurent expansion of that Eisenstein series, again, involving these funny derivatives. So I don't have an arithmetic meaning of it, but in any case, we know that there is some special formula for that next term. So it's just a general idea that one should look at the next layer down, right? Anyway, that's a dream. If you like. Anyway.
Okay. Yeah. Thank you. Sorry.
Okay. Yeah, so.
Any other question? You can't.
Yeah, I don't see anything in the chat box.
Right.
If anyone has any questions, you can just ask Herbert. Well, I guess there are no questions, but a very nice talk, and you gave us a lot to think about. Especially because if people don't know, they're not familiar with the subject. Very nice introductory talk. Very nice survey. So we'll thank Herbert again for a beautiful talk. Okay. Thanks again, and we'll see you all next week.
Okay.
Yeah, thank you.